Alright, I'm going to do number 20 here. 20, we find the net torque on this spinning disc, and we want to find alpha, the angular acceleration. Now in the actual problem it doesn't say alpha, but I added that to it. Once you get the net torque, it's easy to get alpha. So the net torque is going to be the sum of all the torques. So we have a spinning disc spinning around its center right here. And then we have these four forces here. Force 1, 2, 3, and 4. And so we got torques from all of them. So we're going to do this as torque 1 plus torque 2 plus torque 3 plus torque 4. So the net torque is going to be the torque from 1. But remember, torque is always equal to FD times the sine of the angle in between them. So in this case, for torque for force 1, the force is going to be 20 newtons, okay, times the distance. Well, the distance from the rotation point here is 5 centimeters, so that's 0.05 meters. We need to convert these. Times the sine of the angle, but in this case, the distance vector is this way, the angle there is 90. This is the sine of 90. And remember, the sine of 90 is just equal to 1. Okay. Now, let's do for torque from 2. 2 is this one up here at 30 newtons. And by the way, you're given this is a 45-degree angle, by the way. So torque 2 is going to be 30 newtons times its distance from the center here, which is 5 centimeters, times the sine of 45 degrees, because that's the angle between the two, plus force from 3 is 30 newtons, times the distance, but the distance is the radius, which is 10 centimeters, so that's 0.10, times the sine of the angle, but again, the sine of the angle is the sine of 90, because this is a 90-degree angle. All right? And then the torque from 4, if we look at 4, it's applied this way, and the radius vector is this way, so the angle between those two is 0. But what's the sine of 0? 0. So this will not rotate the disc at all, this force 4. You can think of it this way, as if you're trying to open a door, but you're pulling outward on the door's not going to spin. It doesn't rotate that way. So torque 4 is 0, so we can just leave that one off. So the net torque, when we sum all those together, once you multiply all... Oh, I messed up, didn't I? I forgot to put them in. They're not all positive, are they? So we have to look and say, which way are they doing? So let's go back to torque 1. Torque 1 is trying to make it spin in a counterclockwise direction, so it is positive. But the force from 2 this way is trying to make it spin this way, which is also counterclockwise, right? It's pulling here, it's going to make the disc spin this way. That's counterclockwise. But from the force from 3, the torque this way, that's a clockwise direction. This one should be a negative sign up here. So you got to make sure you're careful about putting your signs in, otherwise you're going to get the totally wrong answer. When you multiply all that, you're going to get minus 0.94, and the units for torque is a Newton meter. Because remember, it's a force times a distance, so it's a Newton meter. So that's the net torque on this disc. If we want to find out how fast the disc is rotating, or essentially accelerating, we want to find out alpha. We know that the net torque is equal to I alpha. And the net torque we now have, so to solve it for alpha, the net torque divided by I should give us alpha. Well, we know this is a spinning disc. This is negative 0.94 on the top. The disc is 1/2 mr squared. I look up I in the table on page 300. I come up with that. This is negative 0.94 over 1/2 the total mass of the disc is given to you as 9.5 kilograms, and the radius is 0.1 squared. So we calculate that all out and we get minus 19.8 radians per second squared, or minus 20 radians per second squared with sig figs. So that's the answer to number 20.